Okay, guys, so I want to talk about this problem that Joanna had questions about. She basically has the same name I have. She was asking about problem number 4 out of section 6.3. It basically says the solid with a semicircular base of radius 17, whose cross sections perpendicular to the base and parallel to the diameter are squares. And the problem she's having is she's not really understanding what the problem is or what it's looking like because of the wording itself. So what I've done is I've created a picture for you here. So hopefully you can see both the webcam and the question of the picture. So what you've got up here in this picture is you've got a picture, and I've rotated the axes. So this is actually the positive y-axis. This is the positive x. So I've rotated it to kind of give a 3D view to what's basically a 2D picture. So right here in green, you can see that I have half of a circle. That's the semicircle. Now, saying that the base has a radius of 17, basically I put the center of the semicircle at the origin, and I marked where it crosses the x-axis at positive 17 and negative 17. So that gives it a diameter of 34, but a radius of 17. That means it's also touching the positive y-axis up here at positive 17 as well. Now, the next part says whose cross sections perpendicular to the base. Now, the base is this flat sheet of paper, so it's like this. So perpendicular means coming up off the page, the way that my hand is now tilted. So this is perpendicular to the base. Now, when they talk about the cross section, they mean if I'm able to make slices this way, because now I'm parallel to the diameter. So I don't have my hand like this. That wouldn't be parallel to the diameter. Remember, the diameter runs right here along the x-axis. So parallel, but perpendicular to the flat sheet of paper, the base, they're cutting like this. And they're squares, so the cross sections are squares. So I tried to show sort of a 3D view of a square in blue. So that's where the picture is coming from. So now what we need to do is we need to come up with an equation to describe what's going on here. Okay, so I've talked about what the basic shape looks like. Now we need to come up with the equations. So the equation for the circle, of course, is x squared plus y squared equals r squared, but our r is 17. So since 17 squared is 289, that basically gives us x squared plus y squared equals 289. The question is, should we solve the equation for x or should we solve it for y? To try to figure this out, let's reorient the x and y axis so that it is facing the normal orientation, and so we can kind of see what it looks like from that perspective. Okay, so I've redrawn it so that the x-axis is like we're normally used to seeing it instead of this direction, and the y-axis is the way we're used to seeing it instead of coming out this direction. Now, the green area still is the semicircle right here, and to make it easy, I've just centered it right here at the origin. So it's 17 to the right, 17 to the left, and 17 up. I know it's not to scale. I can't draw. So now let's take a look at what the blue square is going to look like. Remember, your blue square is going to be parallel to the diameter, so parallel to the x-axis, but coming straight up off of the page at a right angle. So it's coming down like this, all the way down. Now, where it intersects the semicircle is at this red line. So I'm going to draw a red line so you can see where it crosses at the axis. So here is what it looks like, just the base of it. Now the real thing is sticking up in the air like this, coming over and coming back down. This is the bottom of the square. So what I need to do is I need to figure out how much area is in that. Now, first off, do I want y's or do I want x's? Well, if I'm going to line up a whole bunch of really thin squares and I'm going to put them together, and I'm going to add up the volume of each tiny little square, I need to know what's the thickness of each little square. If I'm looking at this picture, it's pretty clear that the thickness is this tiny little measure right here of the red line. It's how thick is that red line. Well, that's dy, not dx. And the solutions manual has it the other way around. It works in this case because it's a circle, but if it were any other shape, that wouldn't work. So you need to be careful. Clearly, this is dy. This tiny measure here is a change in the vertical. If it were a change in the horizontal, it would be going this way. That would be dx. Since the differential is dy, then I need to have y variables in my equation. That means I need to solve for x. So I'm going to be using this equation here, that x is the square root of 289 minus y squared. But x gives me the coordinates of a point on this half circle, which means that the coordinates of this point right here are the positive square root of 289 minus y squared and some y value. And these over on this side are the negative of that square root, 289 minus y squared, and the same y value because they're at the same height. It's a square, and because it's centered on the origin, that means this distance and this distance are the same, which means I can just look at this half and double it. So that's what I'm going to do. I need to write the area of the square as a function of y. Since I've decided the differential is dy, I need to have y in the equation. So I need to write the area of the square as a function of y. Well, I know that this side of the square has a length that's basically double the x value, because remember this is 0, x equals 0, this is the positive x value. So if I double this square root, that will give me the full length of one side of the square. So then I'm going to have that the area function is equal to double that radical. So I have 289 minus y squared. And then how do you find, that's the length of one side of the square, how do you find the area of a square? Well, you square the sides. So they're all the same, so I'm going to square that. And that's the function for my area. Now what I need to do is I need to add up all the areas of all the little squares that are coming basically from y down here to y up here. So now we need to set up the integral. That's the next step. So I need to find the limits of integration. Since I decided that the width of this little piece here was dy, that means I need y variables. It means I need y limits of integration. Well, what is the y value at the lowest point? Y equals 0. What's the y value at the highest point? Y equals 17. Again, this would work even if you had mistakenly used dx, because it's a semicircle, so the x distance and the y distance are basically the same. So what we're going to do now is we're going to integrate from 0 to 17. We're going to use our function, which is 2 times the square root of 289 minus y squared, the quantity squared, times the differential, which is dy. So this is basically the common area of the base times the height. Area of the base times the height, that's volume. So when I add all these up, I will get the volume of the solid. So this is the setup of the equation. The rest to do is just algebra and a little bit of calculus. So let's take a look at the next page. Okay, so we set up our equation down here. I've just recopied it up here. Now I did go ahead and square the inside function. So 2 squared is 4. Squaring the square root just lifts it off. And then I pulled the 4 outside the integral. I integrated and got 289y. When I integrate y squared, I get y cubed over 3. So now I need to plug in. So after a little bit of arithmetic, I come up with the final answer of 39,304 divided by 3.